All right, thank you very much. Thanks very much to the organizers for their generosity and hard work. It's great to be here learning about algebraic K-theory with all of you. I guess there's a reminder on the board that there's a party after this, but here's also a reminder that there's a party at 4:30 p.m. right now. Okay, so the title of the party was just announced, and let me start with some context. So there's some words in the title. I want to give some context for why you might care about those, the objects. So one of the great things about K-theory, which we've been seeing all week, is that it's accepting of many things as input. So in particular, it accepts some large class of categories, in particular stable infinity categories as input, maybe small ones. Maybe there's even more than ever. That's not going to be relevant to the talk, but I'll just write it anyway. Okay, so that's some huge class of input, but most classically, the things that you input were the things coming from just good old associative rings, maybe. Okay, and this determines the stable infinity category by taking the category of perfect modules, or maybe you think about it in terms of the whole derived category of modules. And so maybe that's the first class you care about. And inside here, there's a very distinguished class of commutative rings. And here's a lot of special phenomena happens when you study K-theory. So there's this phenomena of Motivic filtrations, which somehow ties this subject into this mysterious world of motives and style cohomology theories, and so on. All this great stuff. Okay, but as has already appeared a couple times, associative rings, that fits in a slightly larger class, which is not all categories, which is associative ring spectra, E1 rings. Those determine stable infinity categories in the same way. You can take the category of perfect modules or the whole category of modules. And I guess we learned from Thomas Nicolaus yesterday the original motivation for this generalization. It comes from maybe Waldhausen, his work in geometric topology, very amazing stuff that we were hearing about yesterday. Right, and then maybe we can consider that there's some kind of common denominator here, which is commutative ring spectra. Okay, and so maybe you care about this K-theory of these objects because of geometric topology. I think at this point in history, it's just socially acceptable to simply be interested in it. For example, because there's so many interesting examples, the sphere spectrum or maybe a group ring on the integers over the sphere spectrum, which sort of ties into this other geometric story, since it's the loop space on S1, group ring on the loop space on S1. And then there's something like complex cobordism, or complex K-theory, or real K-theory, or topological modular forms. Many examples, beautiful examples of commutative ring spectra. And you might wonder, for one reason or another, whether this story of Motivic filtrations and so on, is there any analog in the setting? So maybe I should definitely want to attribute Rognus here. So John Rognus is one of the people that have been thinking about algebraic K-theory of ring spectra for a long time, and he made some specific conjectures and made many computations that sort of suggested that something like this maybe was available, at least in some examples. All right, so that's the context for what I want to talk about. I want to talk about Motivic filtrations and prismatic style cohomology theories in this setting, where the input is a commutative ring spectrum rather than just a discrete commutative ring or an animated commutative ring. All right, so maybe we should first isolate what is the difference between that, what is the real difference between that setting and the classical setting, and that comes from this theorem that we heard earlier this week. So that's this Dundas-Goodwillie McCarthy theorem, which says that for R, a connective E1 ring, or in other words, associative ring spectrum, we have a pullback square, so K of R, that maps to both K of pi 0 of R and TC of R, mapping compatibly to TC of pi 0 of R. And that's a pullback square. Okay, so if you're interested in extending some theory of motivic filtrations on K-theory from discrete things to all things, then you see it's if we know it on discrete things, then what we really have to do is extend motivic filtrations on TC to ring spectra, and then as long as we know the compatibility down here, then we can try to glue it together to get something on K-theory of ring spectra. So the upshot from that theorem in the context of the questions I'm asking is that we can focus on producing motivic filtrations on TC of R, as long as, so assuming we work with connective rings, which I'm going to do throughout today. So we can focus on topological cyclic homology, and if you think a little bit more, actually make even a slightly more of a reduction, actually just, we can just work with the P completion of topological cyclic homology for some chosen prime P. So I'm also going to fix a prime P. The rational part is not so different from the discrete story. Okay, so, right, so to summarize, we're now trying to extend known filtrations on TC of discrete rings, p-adically completed, to that of commutative ring spectra. And oftentimes when the few times I've spoken about this material, I usually try to remind the audience what is known for discrete commutative rings. That's this work of Bottmer-Schulze, and then try to use that as motivation to say how to extend it to commutative ring spectra. But today I'm just going to be cavalier and just say a definition. Okay. So at this point, I'll talk about my joint work with Jeremy Hahn and Dylan Wilson. And that starts with a definition. So a spectrum X is even if pi n of x is 0 whenever n is odd. Okay, so that's not our definition. I mean, the notion of an even number is pretty old, but the definition we introduce is that of the even filtration. And so here I'm going to have so let A be a p-complete E infinity ring. Let me leave some space. So for any such thing, I'm going to define the even filtration on it. The even filtration, fil star eve of A. It's the limit over all maps from A to B, maps of E infinity rings where B is an even E infinity ring. Okay, so B is an E infinity ring, A to B is a map of E infinity rings, and B is even. And I'm going to take the limit over that diagram of the double speed Postnikov filtration of B. Okay, so here I'm taking, this is this decreasing Postnikov filtration, and I've just, I've sped up this, it's sped up to twice speed because nothing's happening in odd, nothing's happening in odd degrees. Okay, that's so that's one definition, and there's a bunch of variants of it that will play a role also. So I could also have said, okay, so there's this empty possibility, and then there's also S1. I could have had an S1 equivariant E infinity ring. I just mean an E infinity ring with S1 action, nothing genuine or anything. Okay, so I'm going to make 4 columns. So the third one is also going to be S1 equivariant, and the last one is going to be cyclotomic, in the sense of a cyclotomic spectrum that you study in topological cyclic homology. Right, and then in this, so for any of these variants, I can do some variant of this construction. I can consider maps to all even such things. So for example, all maps, S1 equivariant maps to even S1 equivariant E infinity rings. And then instead of taking the double speed Poisson filtration on B, I could, for example, take the double speed Poisson filtration on the homotopy fixed points of the S1 action on B. So I'm going to call that Phil star Eve HS1 of A. So maybe I'll remark that when B is even, the homotopy fixed points of an S1 action is also even. So it's of a similar nature to the first example. And I could also do this with the Tate construction of the circle action. I'm going to call that the even filtration for A. And the last one is about TC. So if I have a cyclotomic spectrum, I can try to make some even filtered version of TC. And the formula for that is a little bit longer. I guess I need more space. So it's the fiber of the canonical minus the cyclotomic Frobenius map from these two things that I wrote here. So the double speed Poisson filtration on the homotopy fixed points to the double speed Poisson filtration on the Tate fixed points, Tate construction. Okay, maybe I should have reminded, in case people don't remember, that so in this situation, the topological cyclic homology. So from the work of Nicolas Schulze, there's a formula, which is that it's the fiber of two maps called canonical and Frobenius between TC minus of R and TP of R. And TC minus is exactly the homotopy fixed points of THH, and TP is exactly the Tate fixed points of THH. Okay, so that's what's going on here. So that's a definition of a bunch of filtrations on an arbitrary P-complete E infinity ring, or S1 equivariant E infinity ring, or cyclotomic E infinity ring.
So what about taking, that anti-Nicolas, T structure on cyclotomic spectrum?
Well, I'm not doing that. I'm not sure what to say about. Yeah, I haven't thought about that. Yeah, here I'm just using the usual Postnikov filtration, usual T structure on spectra.
What is the notion of cyclotomic E infinity ring?
Right. So a cyclotomic spectrum. It's a spectrum X with an S1 action. And a map from X to an S1 equivariant map called phi from X to the, so S1 equivariant to the CP Tate cohomology of the spectrum. And so a cyclotomic E infinity ring is an E infinity ring with S1 action together with a Frobenius map of this form. And the main example is that THH of a ring spectrum has such a structure. Right, so THH of a commutative ring spectrum will be a cyclotomic E infinity ring. Yeah.
And in the definition, you take the fiber of
can. So there's these, from this structure, you get two maps from the homotopy fixed points to the Tate construction, the S1 Tate construction. They're also called can, and the other one's also called phi abusively. And I'm just taking the induced maps on the double speed Postnikov filtration of those objects. So for any cyclotomic, for any p-complete cyclotomic spectrum, there are maps called Can and Frobenius from XHS1 to XTS1. And those are the two maps. And TC is the fiber of the difference between those maps. Is that okay?
So this filtration converges in some sense because you use only maps to even.
Yeah, okay, so.
Enough of those two.
Yeah, you should be very suspicious. I mean, it's a ridiculous definition. It looks like a ridiculous definition. I've taken some very specific class, and I'm mapping. It's for both very specific and huge, and I'm just taking all such maps. So there's no reason to think that right now that this will behave well. But let me explain why it behaves well. Maybe I'll go here. Okay, so, well, let me first say a theorem that suggests that it behaves well. And that's that, so if R is a P quasi-symptomic discrete commutative ring, usual commutative ring, then so I can take the even filtration. I could do it for any of those variants. Let me just say it for TC to keep things short. So if I do the TC even filtration applied to THH of R, P completed. So THH of R, P completed, that's an example of a cyclotomic infinity ring. I can do this thing where I map it to all even p-complete cyclotomic infinity rings and do that thing. That's this side, and this thing is the same as the filtration defined by Botmer and Schulze. Let me call it the BMS filtration on TC of R p completed. So that was defined in some very different way. Let me remind you that, so in particular, so what they show is that the associated gradient of this filtration, so GER N is given by symptomic cohomology, R gamma sin of spliff of R with coefficients in ZP N.
So this category of infinity category of maps to even things is not filtered. It doesn't.
It's not filtered. Yeah, it's not even small, but actually the set theory works out, so that you don't actually leave the universe. You don't leave the universe.
Okay, but it is. I understand you can make some cutoffs and so on, but still, it's not. Doesn't which kind of it doesn't have any. Okay. It's,
Right, yeah. Okay. So I'm just saying this is a canonical thing to say, and in any specific example that I care about, the way I'm going to justify that it's something worth working with is that it's given by some very small limit. It's going to be given by a limit over a cosimplicial diagram. But that's to come.
and this filtration is exhaustive and complete, or what?
In good case, in cases that we care about. So I'll say in the cases. I'm going to apply this to THH of some rings, and then I'll assert that for those things that the filtration is complete and exhaustive. Sorry, so it's automatically complete because the Postnikov filtration is complete, and the limit of complete things is complete. Sorry, maybe I should say that. The exhaustiveness is very much not obvious at all. So completeness means that the limit as star gets very big vanishes, and here that's true formally. Things are becoming extremely connective as star goes, as star gets very big.
This is a filtration by sub. You can think of it as mapping to A.
Yes.
So why the inverse limit? You map A to B. Why this? It's not clear that it maps to A.
No, yeah, right. So A only maps to the colimit. So that's the reason. A maps to the underlying thing. yeah, A is mapping to the underlying object. It's not clear that that's an equivalence, but it will be in good cases.
So this, you say it's a filtration, so it must.
Sorry.
What is the fill star EVA? Is it maps to A or A maps to what?
Yeah, so sorry. Maybe it's abusive to say that it's a filtration on A in general. What I mean is that A maps to, so there's always a canonical map from A to colimit as n goes to minus infinity of fill n eve of A. I mean, if everything is, well, yeah, sorry, does that answer the question? So this is you think of it as a big system of like a decreasing thing, which is getting very small as you go to infinity and bigger and bigger, trying to converge to something as you go to minus infinity. And the thing you're converging to is maybe not the original A, but there's a canonical map from A to that thing. And often that, or in cases that will be an equivalence.
So are you sure that the source is A? I mean, for example, suppose that A is already even, then this limit is just nothing.
Yeah, so for example, if A is even, then that map is an equivalence.
No, but for example, in the second case, it's here, you are taking homotopy fixed points.
Yeah.
I mean, the co-limit is homotopy fixed points, right?
Sorry, so this was the case of the non-equivariant stuff.
So the source may be modified.
Yeah, so that's just for the first even filtration, and if there's HS1 and blah, 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 then I have to modify it. Sorry, so another way of saying it is that I'm just declaring in the even case, I'm taking the double speed Poisson filtration, and then I'm right con extending. I'm getting a filtered object by right con extending from that. Any other questions?
You're missing a shift by 2 when on the.
Thanks. Right. Okay, yeah, so for example, in this situation, or you don't have to say it this way, but by this BMS filtration is exhaustive in this situation. So the even filtration, so that map in this case, or the TC version of it is an equivalence. This actually is a filtration on TC of RP completed and not some random object. Okay, and yeah, I mean, so like a surprising feature of this interpretation of the BMS filtration is that like this side, or that construction, in particular this side, it only depends on THH of R P completed as a cyclotomic E infinity ring. In other words, not directly on R itself. So whereas the BMS filtration used some, used some techniques on in terms of R, this is just directly in terms of the cyclotomic E infinity ring. So that's okay. So how do we prove this theorem? How do we control, in other words, how do we control the even filtration in any case? So the way BMS works is that they do descent on the ring R, and the way we study this even filtration is that we try to do descent on this directly on the object THH of R instead. So let me explain the descent property that we use. Okay, sorry, yeah. Okay, so definition is so let a so a map of p-complete E-infinity rings A to B is so evenly free. Okay, and here I apologize for using, well, I'm not going to try to make some optimal statement. There's some issues with p-complete faithful flatness being a real, like kind of technical notion to work with sometimes. So I'm just going to say something that is good enough for me to make statements and not try to make optimal statements right now. So I'm going to define something called evenly free. So what does this mean? It means if for every push out, so p-complete push out diagram, so I take my map and then I push out along some map from A to C, where C is even. So whenever I push out to an even thing, this new guy, this D is also even. And moreover, pi2 star of D is p-completely a free module. P-completely, so it's a non-zero p-completely free module. Over pi2 star of C. Okay.
But zero is even.
Say it again?
The zero ring is an example of even ring, and then the tensor product.
Sorry,
so it's not.
yeah, so I said that wrong. So P completely free module over pi2 star of C, like a faithfully flat free module. So it's zero. If it's zero, then C had to be zero. So I'll just say faith. Sorry. So okay, I'll just say if C is even and non-zero, then what I said is fine.
So what do you mean by P completely free? Like a complete, the completion of three
Yeah.
or modules?
Sorry, P completion of a free module. Thanks.
And C is in which category? Is the module or?
No, it's an E-infinity ring. This is a, P complete push out diagram of E-infinity rings.
Is it derived complete or?
Yes. Derived. Okay, so yeah, so the point of that definition is that the even filtration satisfies descent for those maps in the following sense. So the proposition is that for A to be an evenly free map of P complete infinity rings, I can compute, so the even filtration on A, the even filtration of A, it maps to the limit of the totalization of the cosimplicial diagram given by the even filtration on tensor powers of B over A. P completed tensor powers of B over A. And the canonical map is an equivalence, so it satisfies descent for that map. Okay, and the same thing, so if I had S1 equivariant or cyclotomic, then I could have done any of the variants as well. Okay, the HS1, I could have put HS1 or TS1 or TC there, and I still would get descent. Oh, so this is B tensored over A dot plus 1. So I'm thinking about, so yeah, dot is just standing for a number. Okay. So this is, let me do the proof. So, well, okay, let me at least sketch the proof. So it really suffices to treat the case where A and B are both even. Okay, and everything is right con extended from that case. And so in that case, what we want, this side is just, so let me just do the normal even filtration without any of the equivariant modifications. So we want that the double speed Poisson filtration on A is equivalent to the totalization of the double speed Poisson filtration on tensor powers of B over A. Okay, but so both, as I said, both sides are complete. So can pass to, I can pass to this associated graded statement. So then I'm looking at the map from pi 2 star of A. So the associated graded of the Poisson filtration, that's just the homotopy groups of A. Maybe spread out in different degrees, but we can ignore that. Okay, so I'm comparing that with pi 2 star of these tensor powers. Right, and but by my, because this map is, so in this case evenly free means that B is a free P completely the P completion of a free A module. These derived tensor products, they just their homotopy groups are just computed by the derived tensor, the usual tensor products of the homotopy groups of these things. So this is the same thing as the tensor powers of the homotopy groups of B over the homotopy groups of A.
In some spectral sequence, or?
Well, here I'm just using that. So there's some Tor spectral sequence here, and things are free or flat, so that sequence degenerates. And oh, sorry, and also the evenness means that nothing happened.
There is no differential.
Yeah, right.
That is okay. So you know. So you can interpret it as just fixing an index and taking the limit over. Okay, so just the complex given by the given even homotopy of this is a cyclic in positive degree, then its kernel is the one.
Right.
Okay.
Yeah. Yep, and right, so that's this, and this map is so this equivalence was by my freeness hypothesis, and then this map is an equivalence by faithfully flat descent. Okay, so that's it.
So why evenly free and not something like evenly faithfully flat?
It's so in the paper we do something like evenly P completely faithfully flat, but then there's just something subtle about that because of P completions remaining even and stuff. If I worked in an integral setting without P completions, then it would be very clean and I could just say faithfully flat. But I wanted to match up with the other settings that we're talking about. So yeah. But also interesting, or basically all the examples that are relevant to this talk, they're actually just free. They're just free modules. So. Okay. So maybe let me give an example of. Okay, so this is the method we have for controlling the even filtration. So in this, maybe I should highlight a very important special case, which is that if B is even, then all these tensor powers are also even by virtue of by virtue of this being evenly free, and so all of these things are just given by the double speed Poisson-Gaud filtration. Okay, so maybe I should write that. So in particular, if A to B is evenly free and B is even, then the even filtration on A is just the limit over this diagram of double speed Poisson-Gaud filtrations. Sorry, because all of the things appearing in there are even. Okay, so let me explain how to use this to prove that theorem. So an example. So let me just say, the main example that I'm going to use is that. So there's something called the sphere adjoint X. That means I'm doing something wrong in my life. So that means the monoid ring on the natural numbers. And all right, so I'm going to consider THH of X, THH of that ring. And so that's there's a canonical map back to S adjoint X itself. So there's always a canonical map for any THH of any infinity ring. That if you think about THH as S1 tensor ring, then this is given by the collapse map from S1 to the point. Okay, and I claim that this thing, so its P completion, I guess, is evenly free. Maybe let me not spend too much time justifying it. One way, there's several ways to see it, but the point is that, I mean, this is something very explicit, THH of S adjoint X. If you've thought about Huxley homology of a polynomial ring before, then you'll know that there's some copy of the base ring, and then there's some copy of something that looks like differentials. So there's some copy of this times dx and shifted up by 1. So you can express this as the fiber of a map from S adjoint X to S adjoint X shifted by 2, suspended by 2. And you can deduce from this fiber sequence that that S adjoint X has a cell decomposition, has an even cell decomposition. As a THH of S adjoint X module. Okay, and that's enough. That means that whenever you base change to an even ring, you'll get something, a free module on even things. Okay, maybe let me not say more about that, and then try to use this example of an evenly free map to do something. Sorry, I don't know how to use these words. Okay, so the proof of this theorem, I'll call it the comparison theorem. So our situation is that R is a discrete p quasi-symptomic discrete commutative ring. So I'm going to have to use, now I get to say something about how the BMS filtration works. So this is one of these things that works by quasi-symptomic descent. So they pass to some QRSP thing and then descend down. So let me just say an explicit way you can do that. So we have our ring R, and I can pick a surjection from some huge polynomial ring on some many polynomial generators X, and let me say that some polynomial generator is going to the element P. And now let me adjoin all P power roots. Sorry, I guess everything is P completed. Let me adjoin all P power roots to these variables. Sorry, this is a surjective map. And I'll call the resulting ring S. So this is an example of a QRSP cover of R, a quasi-symptomic cover by QRSP ring. And so I'm going to use this. Let me note that I can also think of this as I have a map from S adjoin all these variables in. And it also makes sense to adjoin P power roots to all of these things. So I have these push-out diagrams like this. And now, so I'm trying to study THH of R. P completed. And I'm going to map in THH of S adjoin all these polynomial variables via this composite top row. Now I'm going to do some maneuvers. So the first thing is I'll push out against the map like this that just appeared in this example, or the many variables version of that. And this push out is called THH of R relative to S adjoin all these variables. Okay, and by virtue of that example, this thing is evenly free, and therefore the push out is evenly free. And so the next thing I'll do is adjoin all P power roots. And so there's a base change formula for THH, which says that the push out is now THH of S, this QRSP ring S relative to this perfected polynomial algebra over S. Okay, and this map, this adjoining these things, this map is simply P completely free. This is simply free. So this thing is also free. In particular, it's evenly free. And this last thing is one of the results in BMS is that this thing is actually the same thing as the absolute THH of S, this QRSP ring. Okay, so the upshot is that this map from THH of R to THH of S is an evenly free cover. And that means that I can compute the even filtration, let's say for TC on for THH of R as the totalization of the even filtrations on so even filtrations of these iterated tensor powers of THH of S over THH of R. But now THH is a symmetric monoidal functor, so this thing is just the same as THH of the tensor powers of S over R. P completed. Okay, and the point of what's happening in BMS is that actually all of the things appearing in here are even. Okay, so this is just the limit over double speed Pavlovkov, or, oh sorry, I was supposed to be doing TC. So I'm supposed to be doing the fiber of the canonical map minus the Frobenius map on tau greater than or equal to 2 star of TC minus of S, let me call it just S dot, to short, to tau greater than or equal to 2 star of TP of S dot. Just because these things are even, and that's exactly, so this is just, that's exactly what BMS declared their filtration to be in this QRSP case. So this is exactly the filtration, BMS filtration on TC of S dot, and their definition, and that matches the definition of their filtration for R, which is by quasi-symptomic descent. So quasi-symptomic descent says that this totalization is exactly computing their filtration on TC of R. Okay, that's the proof. So the point is there's just some there's just some internal THH internal characterization of the covers that they're using to calculate their filtration. All right, that's the comparison theorem. Any questions?
Can you just say quickly why adding roots of x but that thing has a still commutative ring?
Yeah. So if you think of, so it's, maybe if you want to be rigorous, so it's the monoid ring on the natural numbers, and the thing I'm doing is I'm just taking the filtered colimit along the multiplication by p map on the natural number. So this x adjoint 1 over p infinity thing, it's a filtered colimit over some map, some self map of s adjoint x, and it's the. Okay, so I think I just justified this theorem, which suggests that this even filtration idea is at least sometimes not a terrible idea. And our proposal is that so let me first say it vaguely. Our proposal is for some fairly large class of E infinity rings R, the even filtration on, let's say for TC of applied to THH of R P completed should be thought of as the Motivic filtration. Of R P completed. Or in other words, our proposal is let's define the Motivic filtration to be the even filtration for some class of the infinity rings. And so let me say what class is reasonable and why. So a definition is that a connective. So this is only going to be relevant to connective E infinity rings, as far as I know. Connective E infinity ring R is chromatically P quasi-symptomic. If mu tensor R is even, and the homotopy groups of that, so pi 2 star of mu tensor R, that's just some commutative ring, and I'm going to ask that it's p quasi-symptomic. Or I can regard this thing as a commutative ring, and I'm asking that it's p quasi-symptomic. Okay, so maybe I should give some examples first. So I said, I'm sorry. So just all the examples I said at the beginning of the talk are examples of this. So the sphere spectrum, something like a group ring on the integers or the natural numbers, and mu and ku and ko and tmf. So these are all examples of rings whose mu homology is an even polynomial ring. So they're all very nice. And probably there are others. And right, so the theorem. So why is this a reasonable class? Well, we basically show that for any chromatically p quasi-symptomic connective E-infinity ring, there exists an evenly free map THH of R P completed to B. So there's a map of P complete cyclotomic E-infinity rings where B is even. Okay, so that means that all these even filtrations on the THH of it can be computed via some cosymposial object exactly like happened here. And it's not some crazy thing. And in particular, yeah, so you can use this to show that the filtration will be exhaustive, for example, and so it's well behaved in this situation. And so I don't want to say anything about how we produce this B. Maybe let me just say it's quite different than the way that that happened in this discrete ring situation from the BMS perspective. So here the trick was to pass to some QRSP ring by adding infinitely many p power roots, and that's something that you can do to very formal elements like these polynomial variables. But if you have some arbitrary or some other E-infinity ring and some elements in there, it's in general not possible to join p power roots. That's some fact in higher algebra, and so that technique is not available to try to produce even THHs. So there's some other technique that we use these even B's still come from the theory of THH, but we produce them in some other way. All right, so yeah, so instead of going more into how we do that, let me just give 2 examples that we've been studying in more recent ongoing work. So at this point, I'll describe some ongoing work with Sanath Developurkar and Jeremy Hahn and Alan Yuan. And so the examples, so a couple of the examples that we've been thinking about are just some basic things to get started are S, so let's say THH of S. That's the same. That's just S again, actually. It's S as what's called with a trivial cyclotomic structure. And so let me give an example of a way to work with that. If you just map to mu with a trivial cyclotomic structure, then that's an evenly free map. Okay, that's just because the complex cobordism of an even ring is a free module. It's a polynomial ring. So that's one cover that you can try to use to study THH of S or TC of S. And maybe let me also say that for THH of mu, you can use this collapse map back to mu this is also evenly free. This is for a very similar reason to this polynomial ring example I discussed earlier. So here, let me say this is at least an S1 equivariant map of E infinity rings. So maybe this is not, so at least an S1 equivariant map. Maybe not a, so I think we can actually produce a cyclotomic structure on MU for which this is a cyclotomic map, but that's ongoing. Let me not assert that confidently yet. But this is an S1 equivariant map. It's at least good enough to compute something like the HS1 or TS1 even filtrations for THH of MU. Okay, and let me say something about what these maps, so these maps are supposed to be used to describe something about these invariants, THH and TC minus and TP and TC of these objects. And let me just say something along those lines. And I'd like to say it sort of in this language of prismatization that Johannes has been talking about. So I'd like to just give a slightly different perspective on some of this even filtration stuff. So let me make a definition. The definition is that if A is a P-complete S1 equivariant E infinity ring, then I'll define an FPQC just a FPQC stack, a stack on ordinary on just usual commutative rings. Right now I'm calling it pi HS1 of A. And it's similar to the even filtration definition. I'm going to take, but now it's a colimit in the geometric setting rather than a limit in the algebraic setting. I'm taking the colimit over all maps from A to B, where B is even. B is an even S1 equivariant E infinity ring. And instead of taking, so now I'm going to take, I want to consider pi 2 star of BHS1, and then I'll take a formal spectrum of that. So here, SPUF is with respect to the ideal P plus the ideal given by the kernel of the map from pi 2 star of BHS1 mapping to pi 2 star of B. Okay, so there's some orientation class in pi minus 2 here. This is a principal ideal. Okay, so that's some stack, and basically the way you should think about this, it's a stack such that coherent cohomology of this thing is computing the associated graded of the even filtration on A, the homotopy fixed point version of it. Sorry that I'm going a bit fast right now, but I have a couple minutes, so let me just try to state the results. So,
it is stack on A is on this in this sense of infinity.
No, it's just an FPQ stack on commutative or discrete commutative rings.
But you apply to A.
Oh, sorry. This is a name for the stack. This whole thing is a stack. No, not the value of the points, and it's the colimit over these usual stacks, both of these rings.
Essentially, what the stack you like quotient by the GM action? No.
Oh yeah, sorry. Good, thank you. Mod GM. Thanks. So there's a GM action coming from the grading of this object.
So is it an action of GM before colimit also?
That commutes with the colimit.
Okay, so it's a limit of usual. But since you quotient by GM, it is not. It is also an Arpon stack. I mean, it's also an FPPF stack, or it's both FPP. There is some subtlety of passing to. Or maybe it's okay. It's,
Okay. And then, so the case I'm really interested in is that when R is a P quasi-symptomic, chromatically P quasi-symptomic E infinity ring, and I apply this to pi HS1 of THH of R, be completed. Let me just give that a name. So to just be suggestive, that's R Nygaard hat. So if this is supposed to be analogous to some object in the prismatization story, but it's something which knows the sort of the completed Nygaard, the Nygaard completed prismatic cohomology. Okay, and sorry, I'm just going to take 2 minutes to state the final result. Which is that these covers that I described for S and MU, we can use them to describe this stack in those cases.
You could take out the phase constellation.
You can, yeah. So there's something subtle about that. So yeah. So yeah. Let me get back to that after. So there's something subtle about that. So the theorem is that. So let me describe I'm going to describe the points of the stacks associated to S and MU. So for T, P nilpotent ring. So if I take this Nygaard stack, completed Nygaard stack associated to S, then its T points are just the groupoid. It's just a groupoid of a formal group over R. Formal group in the topologist sense, so smooth of dimension 1, and a section from spec R. In other words, the stack is the universal formal group. And MU Nygaard of T. So this lives over S Nygaard by virtue of the fact that MU is an S algebra. So it in particular classifies a formal group and a section. And then the other data is somewhat funny. There's a symmetric 2 cocycle. So there's a map from G times G to BGM. So a line bundle on G times G, and that satisfies, it has some structure, which is that it's a symmetric 2 cocycle. And there's one further data, which is that once I have the symmetric 2 cocycle, I can, and my section, there's a line bundle given by restricting that symmetric 2 cocycle to the section S times G. And there's another line bundle which is just given by associated to the 0 section of G. And there has to be an identification between those two line bundles. Okay, and I slightly lied. This is just, it's a full subgroupoid of this thing where the property is just some local triviality condition on this symmetric 2 cocycle and this identification.
It goes into where, symmetric 2 cocycle?
Sorry?
The symmetric 2 cocycle is going to where?
To BGM. The classifying stack for line bundles. So it's a line bundle on G times G which satisfies some kind of symmetric 2 cocycle condition.
Okay, in the higher sense.
In a higher sense, yeah. Okay, sorry, I've gone over time. So yeah, that's just some interesting structure that we've seen arise so far in some simple examples. And I'll stop there. Thank you.
Yeah, are there any questions? So what's the idea to prove what?
Idea to prove 1. So the idea in both cases is to use these covers in order to compute the stack. And so the second one is a little bit more complicated, but the first one is not so hard. You have to so the descent the descent here is basically the Adams-Novikov descent. You're looking at powers of mu over just tensor powers of mu. And if I just did pi star of that, you'd be seeing the moduli of formal groups in the usual way of in chromatic homotopy theory. And then with the HS1 is where you get the section.
So you get like the Lazard ring by.
Yeah. So at the first step, you get the Lazard ring plus a power series coordinate, and then you see the isomorphisms. And yeah.
So what would be the stack associated to small TNF?
I don't know. Yeah. So yeah. Doing other things, yeah, I don't know, but good question.
Is stack associated to what?
TMF.
Why did you write T and R then in the first thing?
Oh, sorry. That was because I'm a bad person.
Yeah, so if you apply this construction to the usual algebra, do you get some version of the usual Nygaard step?
Yeah, right. So yeah, I should have said that. Yeah, so it's the Nygaard stack. The hat means that you've pulled it back from A1 mod GM to A1 hat mod GM. So you sort of you can't see the underlying. It's smaller, yeah. So so I mean we're still, this is the sort of still ongoing project, and we're trying to make sense of kind of the full prismatization picture, but there's various subtleties having to do with Nygaard completion, because that's what so this is what we can state cleanly right now, but hopefully there's some way to also get the bigger thing.
So if you can see the Nygaard filtration, the HS1 fixed points, does this mean that in DHAs you see that graded piece for the Nygaard filtration?
Yeah, that's right. Yeah. So there's also some clean definition. Just if I did not put HS1 here, that would be some version of this like conjugate stack.
So can you clarify why this definition of MU is like the correct definition of what technologies?
I mean, so the way, I guess it has to do with how we construct these Bs. So the first thing to say is that is an important point that S to MU is an EFF cover. And so the way we try to compute all these things is always like first descend along the map, first tensor to MU, and then try to do something. So the first descent you should try to do is tensor up from S to descent along this map. And then, I guess the idea is that then if you're in the even situation over MU, then even things over MU is something where we could actually do something. Do I have a short answer for this? I guess maybe I don't have a short answer. That's where we we first descend by tensoring along this map, and then we want to make some constructions, and we can make these constructions exactly when we have even algebras over MU and not in general. Yeah. Yeah.
So presumably there should be like the TS1 version of this stack, right? And there should be 2 copies of it in this one. You know how to see it, or what you would expect, at least to see.
Yeah, so I don't have a clean answer to that right now. So someone else also asked about TS1. Yeah, so I should. There's just something weird about. So here, when I did this, I completed at the variable t. I completed at the variable that you invert, and so if I want to do something for TS1, then I have to not do that completion. And so there's something hard about that. There's something hard about that. And so I currently don't have there's some things you can try to play around with what TS1 looks like, but I don't have some clean story about what the TS1 stack is right now.
Is that it? Are there any more? Okay, if there's no more questions, then I can see.